Hello everyone, my name is Andrea Pranno. I'm a research fellow at the University of Calabria. This work was carried out with the contribution of the Professor Greco, Lonetti and Nevone Blasi and Doctors Leonetti and Maio. In this work, a numerical investigation via diffuse interface approach has been carried out to analyze the cracking phenomena in ultra-high performance fiber reinforced concrete with embedded nanoparticles. The presentation is organized in this way. Firstly, I will start by introducing the topic in the motivation. Next, the theoretical background of the adopted numerical fracture models has been briefly recalled. Then I'll focus on the numerical results, and I will end with some concluding remarks. The fracture behavior in concrete structure is commonly characterized by the complex interplay of irreversible processes such as defect nucleation, microcracks grow, and other physical phenomena, which leads to a complete localized damage state with macrocrack propagation. Recent progresses in nanotechnology have clearly shown that the incorporation of nanomaterials within concrete elements leads to a sensible increase in strength and toughness, especially if they use it in combination with randomly distributed short fiber reinforcement, as for ultra-high performance fiber reinforced concrete. In the literature, several computational type investigations on the cracking phenomena have been presented involving different modeling techniques based on two different groups, discrete and smeared fracture approaches. The first ones assume a traction separation law to simulate the nonlinear fracture process along the extension of the real crack, where the material keeps its ability to transfer the stress. Such models have been extensively used to predict crack propagation in quasi-brittle materials because they are very effective for accurately representing the real crack pattern, but they need a continuous change in the mesh topology, especially if the crack path is not a priori known, thus requiring additional remeshing procedures. The second group of models consider the fracture processes as a gradual diffuse degradation of the material integrity through a stress-strain constitutive relation, thus smearing out all the discontinuities over the continuum. Such models avoid the explicit insertion of the discontinuities in the topology of the finite element mesh and avoid any remeshing algorithm, but they can be subjected to local instabilities due to the ill-posedness of the resulting boundary value problems. In this slide, the theoretical background of the proposed diffuse interface approach is briefly explained. It is based on an interelement fracture approach to simulate the crack propagation, and it relies on the variational formulation defined over a discretized domain whose the kinematic is enriched by interface elements placed along the boundaries of the mesh. In the weak expression, you can note an additional contribution, that is the virtual work of cohesive traction, which is defined on the internal mesh boundaries. This form has been derived under the simplified assumption of quasi-static loading, small deformation, and linearly elastic bulk materials. It follows that the nonlinearity source is only in the cohesive term. The interface behavior is governed by an intrinsic cohesive law. The softening is expressed in terms of a single scalar damage variable, which depends on the maximum effective displacement jump over the whole temporal history. Now, the proposed numerical model implemented to simulate the failure in ultra-high performance fiber-reinforced concrete beams is described. In order to model all failure mechanisms together with their interaction, two different models have been incorporated in a bidimensional finite element framework. The first one is the diffuse interface cohesive model used to capture the nonlinear cracking processes in the concrete phase, for instance, the shear and the flexural cracks, concrete crushing, and concrete cover separation. The second one is called embedded truss model, and it allows to capture the interaction between the concrete and the steel bars. In detail, 3-node plane stress elements are used to model the concrete, and 2-node truss elements are used to model the rebars. Moreover, the two meshes are not geometrically coupled, meaning that the truss and the concrete nodes can move independently to each other. In this way, the effect related to the artificial crack arrest is avoided, and the bond between the concrete and the steel is guaranteed by a bond-slip relation for the tangential traction. The adopted diffuse interface model is implemented by using a 4-node zero-thickness element randomly inserted along all mesh boundaries. These elements are equipped with a traction separation law for non-enhanced ultra-high performance fiber-reinforced concrete. This is a trilinear softening model able to capture the tensile failure of fiber-reinforced concrete, initially proposed in Park et al. In the 2010 for functionally graded FRC, and here adapted to the specific case of ultra-high performance fiber-reinforced concrete with embedded nanomaterials. In particular, as can be seen in the center of the slide, all the microscopic fracture mechanisms of fiber-reinforced concrete are taken into account, including cement paste microcracking, matrix aggregate debonding, and fiber pull-out. The first two linear descending branches of the adopted trilinear softening model are associated with the initial and the total fracture energies of nano-enhanced ultra-high performance concrete, whereas the last descending slope is related to the additional energy required to the bond and the pull out the fibers from the cement paste, corresponding to the difference between the total fracture energy of the nano-enhanced ultra-high performance fiber-reinforced concrete and the total fracture energy of the nano-enhanced ultra-high performance concrete without fiber reinforcement. The present numerical simulation involves small-sized, ultra-high performance fiber-reinforced concrete beams subjected to a 4-point bending test analyzed in Meng and Kayat in the 2016 from an experimental point of view. Here were considered 3 different mixtures, one without nano-enhancement, which is taken at the control 1, and 2 mixtures containing the 0.05% and the 0.1% of graphene nanoplatelet reinforcement. Both physical and the mechanical properties of the graphene nanoplatelets and the steel fiber reinforcement are reported in the table on the right. The load versus mid-span deflection curves highlights a good agreement between the experimental and the numerical loading curves for each the investigated beams, underlining that the adopted traction separation law, if suitably calibrated in terms of inelastic cohesive parameters, is reliable for determining the structural behavior of both normal and non-enhanced ultra-high performance fiber-reinforced concrete elements with low nanoparticle contents. With the purpose to investigate the mesh influence on the fracture behavior predicted by the diffuse interface model, a sensitivity analysis is performed by varying the mesh size. With reference to the already examined control ultra-high performance fiber-reinforced specimen, the numerical results shown on the right of this slide highlight that the global structure response in terms of load versus the mid-span deflection curve is almost independent of the mesh size. Then the proposed fracture approach has been employed to simulate the crack formation in steel bar reinforced ultra-high performance fiber reinforced concrete enhanced with graphene nanoplatelet and subjected to a symmetric 4-point bending test. The related geometrical configuration, loading condition, and constraints shown in this slide are taken from the experimental test performed on standard reinforced concrete beams found in Gao et al. In the 2004. The main mechanical parameters of both the ultra-high performance fiber reinforced concrete and the steel materials are listed in the table on the right. As can be seen in the control beam mesh, to reduce the computational effort, the cohesive elements are inserted all in a large region dominated by the concrete tension shear behavior, since the concrete crushing is not accounted for. No cohesive elements are inserted in the correspondence with the truss element to avoid a preferred crack path, and an example of the numerical results obtained is reported in the animation, in which one can be clearly noticed the formation of multiple cracks. In this slide, the numerically predicted structural response is reported in terms of total load versus mid-span deflection curves for all the 3 concrete mixtures. As expected, the obtained loading curves show greater load carrying capacity with respect to the conventional reinforced concrete beam, with increasing strength values for increasing content of embedded graphene nanoplatelets. In particular, the typical trilinear behavior of the steel bar reinforced structural elements has been observed for all the analyzed cases. The role of the graphene nanoplatelets under service condition was investigated by examining the deformed beam configuration at a load level of 45 kN, corresponding to the early stage of the crack propagation at the bottom of the beams. It can be seen that the cracking patterns are not completely developed compared to those obtained at higher loading levels. The analysis of the crack patterns has been more deeply investigated by computing the crack spacing, the average crack width, and the beam deflection for different content of graphene nanoplatelets, as reported in table on the right. At surface condition, the crack spacing is not influenced by the presence of nano-reinforcement, resulting in being equal to 100 mm for all the investigated mixtures. Contrary to what happens for the crack spacing, the average crack width is strongly influenced by the nano-reinforcement, leading to crack width reduction equal to 30% and 55% for the two different graphene nanoplatelet content investigated and compared with the case without nano-reinforcement. Then, the tension stiffening effect can be better highlighted by analyzing the deformed configurations at a load level of 65 kN, corresponding to the first yielding of the tensile reinforcing bars of the beam without graphene nanoplatelets. It is worth noting that, owing to the higher fracture toughening effect provided by the embedded nano-reinforcement, with the addition of the 0.1% of the graphene nanoplatelets, a significant reduction of the crack pattern development is experienced compared to the other cases. Specifically, a crack width reduction of the 14% and 31% respectively for the two investigated content of nano-reinforcement is obtained, together with a beam deflection reduction equal to 13% and 27% compared to the case without nano-reinforcement. It clearly highlights an improvement of the overall mechanical performance in terms of increasing bending stiffness as the nano-reinforcement content increases. Furthermore, the axial stress distribution along the tensile reinforcement bar of the three simulated ultra-high-performance fiber-reinforced concrete beams has been reported for the same load level equal to 65 kN. The reported trend is characterized by lower values of the average rebar stress for higher values of the graphene nanoplatelets content, and it confirms the increase in the tension stiffening effect for increasing fraction of the nano-reinforcement. In particular, the reduction in the maximum stress associated with the 0.5% and 0.1% of graphene nanoplatelets are of about 11% and 23% respectively with respect to the case without nano-reinforcement. In this work, the proposed modeling strategy is able to accurately predict multiple crack initiation and propagation phenomena to preserve the discrete nature of the fracture processes and therefore to capture the real complex crack pattern in terms of both crack spacing and crack widths. The numerical outcomes have demonstrated the accuracy of the proposed model in predicting both the straightening and the toughening effect of embedded nanomaterials in terms of global load deflection responses and associated crack patterns. An increasing of the first yielding load level and the absorbed energy up to 11% and 20% respectively are numerically predicted for beams with the highest considered graphene nanoplatelets content. The role of the nanomaterials on the tension stiffening effect has been demonstrated by analyzing both the final crack patterns and the associated stress distribution maps. The addition of low volume content of nano-reinforcement is able to increase the ductility of the simulated beams. In fact, the addition of the 0.05% of the graphene nanoplatelets allowed a crack width reduction of the 14% together with a stress reduction along the steel bars of the 11%. And the addition of the 0.1% of graphene nanoplatelets allow a crack width reduction of the 31% together with a stress reduction of the 23%. Thank you for the attention.